last topic for waves is stationary waves. Got that?
Yes.
Yeah. Okay, so stationary waves. Not too difficult this lesson. The last two lessons were more difficult. So to start off with stationary waves, we have this new type of wave called a standing wave or stationary wave. Have you heard of this before? No? Are you sure? Okay. It's a wave that oscillates in one constant position. It can arise in a stationary medium as a result of inference between two waves travelling in opposite directions. So what does that mean with a picture? Maybe you've seen this picture before. I can try and find it online, a video.
Is it the guy in the middle, like the water tank, and then he like
No, not that one. It's the one where you would have like a wall here, and then there's a rope here, and this is oscillating up and down, and it makes a wave appear in the rope, and then the the second wave that reflects backwards looks like the first wave but just upside down. Have you seen this? There's a I'll get the video for it as well. Have you done this one in class? No? I'll try and get the video for it as well. So
stationary wave just mean contact wave.
the wave that's not propagating forwards or backwards, it's just kind of bouncing between up and down positions. I'll show you with a video.
Isn't the rope moving forward and then
Well, the rope is tied against the wall.
I mean not the rope, like the wave on the rope is going forward.
It is, and then it reflects against the wall. But it's done in such a way that the wave, it doesn't look like it's moving through the rope. Instead, it's just kind of flipping up and down. I'll show you with a video. No. Did they reply to you?
No.
Oh goodness, okay. Lab, there you go. Here it is. It'll take a second to load. So all you really need to do this is just a string and a little motor. Maybe I have a picture here as well. Yeah, I'm going to try and get the video for this, but the wave is just moving up and down, not left and right. If I can get a video, it would be great. It looks like I can. No, okay. We'll have to look at the video later, but you can use your imagination. With the string, it moves up and down like this. So this is a stationary wave. So the definition, I know it's a little bit difficult, but when I say it oscillates in one constant position, I mean like the wave is here, and it's not propagating forwards or backwards, it's just here, and all that's happening is the peaks and troughs are turning upside down. And the reason for this is when the wave tries to move forward, it reflects and moves backwards. And it'll be upside down when it comes backwards if you have everything set up right. But anyways, just for the moment, can you write that definition down? And you can draw the picture, it'll be useful as well. Is there any assignment today?
No, math quiz.
Let's just quiz
At what time?
next class.
Think this could be the reason?
Maybe like yesterday they can get up.
Maybe they were studying at night, so they couldn't.
Yeah, this is what I mean. This might be the reason. Okay. So what's your excuse for being here? You don't need to study. Oh, you live here, right?
Well, Patrick can apply for university, but he had a kind of poor attendance.
You can apply for whatever university you
Oh.
want. The real question is, can you get an offer? That's the real question. You can apply to anything. The attendance is more of a problem with visa.
Visa.
Yeah. Okay, you got this? Yeah? Okay. So, that's an example of a stationary wave. So, stationary waves have two main parts. What's called the node is the point in the standing wave where the wave has minimum amplitude. So if we go back to the picture, I don't think I have the video. No, rats, I don't. Okay. But you can imagine this is moving up and down. So the point right here, you see this one here? That looks like it's not moving. So this is called, this point and this point, they're called the nodes. And this point here, that's moving up and down the most, that's called the antinode. So the node is where there's no amplitude, basically. And the antinode is where there's maximum amplitude. So in the picture, the nodes are in between here. And the antinodes are the ones that are moving up and down the most. Okay, so I need this definition, and you can draw this picture as well for nodes and antinodes. Are these words, Kareem, are these words you've seen before in high school? Yeah, node and antinode. So you've seen standing wave before?
No. Like we studied note like in wave, like how it's destructive and then like a node, right?
Oh, okay, okay. got that? Yeah, great, great. Okay, so we got node and antinode. So if the distance between the nodes or antinodes is known, then you can know what the wavelength is. So if we just go back to, well actually maybe I'll draw it here. I got my picture still. Yeah. Where's my pen? So if you look here, imagine you know the distance between the two antinodes here. We'll call this distance D. Or even the distance between two nodes. We'll call that D as well. So let's say we know the distance between the antinodes. What would the wavelength equal? Would it equal D or not?
No.
It's not going to be quite D.
It has to be, isn't it? Like not the dotted line.
If it helps, what about if I do it from a node to a node? The wavelength will be 2D.
Yeah.
Does that make sense? So if you know the distance between the nodes and the antinodes, you can know the wavelength. It's just twice this.
So it's two nodes, right?
Node, yeah, node to node or antinode to antinode. The wavelength is twice this distance. Yeah. So I drew that. So I at least want you to write that down. That the wavelength is twice the distance from node to node. Wow, who have I got? Sophie. What happened to you?
Bus didn't
Bus
come in.
trouble?
Yeah.
You didn't see Amanda or Grace out there, did you?
No.
No.
Opposite direction.
Ah,
Or antinode, right?
yeah. I say, Sophie, maybe you could leave one page in your notebook and then go to the next page. I'd say, how much have you written? About one page?
Half a page.
Half a page?
Yeah.
If you leave about half a page, you can get it later. Okay, continue. Okay, so if the string is held at both ends, hang on, come on. Yeah. So if the string is held at both ends, forcing no movement at the ends automatically become nodes. The length of the string then becomes a measure of which waves the strings will entertain. The longest wavelength is called the fundamental. Okay, so before you write anything down, let me just draw what I mean. So you could have, for example, somebody moving the wave at the end, moving it up and down like this. But if you think about like a musical instrument, like a guitar, the ends are fixed. So that means that these must be nodes at the end if they're fixed. Okay? Whereas if I'm moving it with my hand, well, this here must be a node, but this one here could be an antinode. Or also it could be a node as well. But we're going to see in different situations we'll have different ends. So if it's like a string from a music instrument, the ends must be nodes. So you could have a few possibilities. You could have like one wave like this, or maybe you could have two waves like this, and so on. You could have three waves. So this is the biggest wavelength you can have. I can't make it any bigger because if I try to make it bigger, like for example, like something like this, then I have a problem because it needs to be fixed here. So the biggest wavelength is called the fundamental wave, and then all other waves are called harmonics. So that's a harmonic. Now if I try to fit in 3, 1, 2, 3, that's a harmonic as well. These are all harmonics. So this vocabulary, fundamental is the one with the biggest wavelength, and then harmonics, they have smaller wavelengths.
Usually the biggest wavelength will be the one.
Yes. Ah, well, hello.
You're Steven.
What happened? You're late because you went to Starbucks?
No. Because of the car. I
The
go there.
car.
Yes.
You drive now.
No. We come here at 4. 4.
4.
Yes.
4.
Yes.
4 a.m.
No. I mean the longer one is at 4.
Oh, okay. 20 past.
Yes.
So why are you only here now at 1/2 past? Where have you been for 10 minutes? Oh, great. You're late for class and you went to Starbucks?
But I'm working.
Doesn't help. Alright, so, yes.
Like the one with the longest wavelength will be in the middle, right? Will it not?
In the middle?
Like in a guitar, the one with the biggest amplitude will be like in the middle, right? Of the string. The fundamental wave.
Yes, she's not much better than you right now. You need to talk to them if you want some notes. I wouldn't necessarily say in the middle, like it fills up the string.
Okay.
Yeah.
So wait, like the fundamental and the harmonic wave, are they like in one string?
Oh yeah, the same string. So you can have a fundamental or a harmonic.
So the wavelengths are not the same.
No. Harmonic wavelengths get smaller. The fundamental is the one with the biggest wave. What's this? This is what you're missing right now. Okay, so what I really just need. Listen, hey. What I really just need is the 2 words I have in red. I explained them with the picture here. So you can draw the picture. You don't have to write this down. So I think there's too much English here for you to write down. I think a good picture would be helpful. So for example here, that's the fundamental, and then let's draw, this is wavelength lambda, and then here, this is wavelength lambda over 2. It's half of this wavelength. If this one is lambda, then this one here, its wavelength is the lambda here divided by 2. And this is called a harmonic. And you can have more harmonics. You can have the first harmonic, the second harmonic, the third harmonic, and so on. Okay. Of waves, yes. Yes. It should be okay. Alright, can you write those 2 words down and maybe even draw the picture? Just to be careful with the English here, this fundamental, well no, I'll get to that in a minute. So just draw these 2, please. You got that? Yeah. No? What's taking so long? You've been here the longest. I just need fundamental and harmonic. What?
I think there are explanations.
I'll get you a nice picture here. Oh, rats. I drew my picture wrong. I'm so sorry. I'm so sorry. I told a dirty lie. That's not the biggest wave I can draw. I can actually draw one which is this big, and you can't actually see the rest of it, but that's actually the biggest wave I can draw. But here, I think this beautiful picture would be much better than my picture.
But I thought the lambda is too low.
In this one here, the lambda would be
Twice that, right?
it's twice this distance, yeah, which is the full distance there. I think this is much better. I shouldn't try to draw things. So the first wave there, that's the biggest one I can actually fit. I forgot about that one, I'm sorry. So the wavelength is actually twice that distance we were saying earlier. Please note that the fundamental is also called the first harmonic. And then the second harmonic is the next smaller wave I can fit in, and then third and fourth. I actually wonder if I have a picture. Come on. Come on. Of course I have the picture, of course. Oh, what a fool. Right, okay, so there's a beautiful picture for you. First harmonic, second harmonic, third harmonic. Got that? Yeah. I'm tired because I was watching Batman until 3 a.m. True story.
Why?
Because he's Batman.
It's YouTube too.
Of course. Alright, can I continue?
Yes.
Yep. Right, so you can get sound waves not just in a string but in a music instrument I think this is a clarinet, like a flute, something that you play, a pipe. So I think again I'll draw this one here. There's two key different pipes. You can have a pipe like this, which is closed on one side and open on the other side. Or you could have a pipe which is open on both sides. Okay. So let's first look at this pipe here, which is closed on this end and open on this end. The key thing I want you to know about these pipes is that at a closed end, you always have a node, and at an open end, you always have an antinode. Oops. And I think I say that here actually. So there'll always be a node at the closed end and an antinode at the open end. So please make note of that. That's the most important thing for these pipes here, that it's closed at the node. The node is at the closed end and the antinode is at the open end. Yeah? Got that? Okay. So, what I would like you to do before I do it is I want you to try and draw, wait, this is the fundamental wave. So what's the biggest wave you can draw in this? And remember, this side must be a node and this one must be an antinode. So what's the biggest wave you can draw? Yes. So the biggest wave I can draw is one that has a node here and an antinode here. So that's like this. Let's say this pipe, its distance is d. What would the wavelength be for this wave?
2 or 3 of that, right?
No, simpler than that.
Oh, twice of that.
No. Anybody?
Half of that.
The wavelength for this wave?
Yeah, isn't
No.
it?
Half.
No, 4D. Because look, use your imagination. If this is the wave, it's, is it 4D or is it 2D? Yeah, it has to come back down and go all the way down and then all the way back to the middle. So this piece from middle to top, that's only a quarter of a full wave. So it means in this picture here, the wavelength is 4D in this picture. So that's the fundamental. Can you try and draw the next harmonic? What's the next wave you could fit inside here? Well, let's see. It would start here, and I need to finish on an antinode. So I don't think it'll be that. It'll go up. Up, down. Ugly. Up, down to the middle, and then back down here. So this is the next harmonic I can fit in. So for this wave, can anybody see what the wavelength would be?
Half.
One over 2.
Wait. Think for one moment. How much of the wave fits in the pipe? So in the first example, how much of the wave fit in? A quarter of the wave. In the blue example, 3/4 of the wave fits inside. So the wavelength will be 4/3D. Yeah? Okay, let's go back. Look at the black wave. How much of the black wave fits in the pipe? A quarter of it, yes?
Half, yeah.
A quarter. So the wavelength is 4D because a quarter fits inside. The blue wave, how much fits inside? 3/4. So the wavelength is 4/3D. Because it starts in the middle and goes up to the top, back to the middle, and down to the bottom, but it doesn't go back to the middle. So it's only 3/4. Yeah? And now one more, I want you to draw the next harmonic after this. Yeah, it's just a wave, isn't it? Draw it for me. I'll do it in green.
Maybe 4/3.
Maybe. Who knows? Okay, so the next one I can draw, let's see, I'll start in the middle. So I'll get let's try that again. in this green wave, I've drawn, is that
One
right?
wave and then one.
Or have I made it too much?
I think it's right.
I've drawn 5/4 of the wave inside of it. So it'd be 4/5 D.
Isn't it 5/4D?
Maybe. Hang on. How much have I drawn? 5/4. No, 4/5.
That's the wavelength.
Yeah. Because I've drawn 5/4 inside. So you can kind of see a pattern what's happening. On the top, I always have 4, and then on the bottom, what do I have?
One.
An odd number. 1, 3, 5. So the next one would be 7, and so on. Yeah. So this is the first harmonic. The fundamental is here, and then this is the. Now I think, yeah, I'll get a picture up for this. Anyways, that is closed at one end and open at the other end. So next we'll have a look at it as open and open. Well, maybe I can find you a nice picture instead of my ugly picture. Fundamental, harmonic, open, closed, tube. This looks pretty nice. So the first one, this was when I got 1/4 inside. This one is when I got 3/4 inside, and this one's when I fitted 5/4 inside. So if you need a beautiful picture, there's a beautiful picture for you if you want to try and draw that one. Yeah. Beautiful, beautiful pictures. Okay, have you got this one? Can we go to the next one? No. No, okay. Yes.
What's the
This one here? The formula? Is it? Yeah, the wavelength is 4/5 D.
Just name fundamental harmonic.
The first one is called fundamental, and then the next ones are called harmonics. See this red one here? That's called fundamental. And then this blue and this green, they're called harmonics. But Amanda, sometimes people call the fundamental the first harmonic, but I usually call it fundamental. Okay. Well, we have a look at the next one, which is open at both ends. So what do you have at each end? A node or an antinode if it's open? What do I have? Node or antinode? Must be an antinode, and here must be an antinode. So let's draw the biggest wave that has an antinode at each end. So let me think. The biggest wave I can draw would be this one, and it's vibrating up and down. So you know it's going like that as well. If this is D, then what's the wavelength here? Anyone want to try and guess?
4E.
Don't think it's 4.
4/3?
I I don't think it's that either. I think it's just 2D, because if you look at the wave, it goes from top, middle to bottom. And if I draw a wave here, look,
Oh, yes, the
if I go top, middle, bottom, that's half the wave. So I think the fundamental is wavelength will be twice the pipe length. Okay. Got this? Well, let me find you beautiful pictures. Okay, so beautiful pictures. The next one, I'll just show you the picture. So this is the fundamental, which I just drew. This one here, now we can do the formula together. So how much of a wave do I have in the pipe that's open at both ends? No,
The wavelength is 1.
I know, but how much of I want to know how much of a wave do I have in this pipe? Do I have one full wave in there?
Yeah.
No.
Half.
No.
Isn't it 1?
Is it? Oh, sorry, my mistake. Apologies. Yes, we have one full wave in here. So what's the wavelength here? It's the length of the pipe.
One full wave.
Yeah, one full wave. So top, bottom, top. One full wave. Yeah. So here, the wavelength equals D.
Which one do we need?
Well, you need all of them. How many waves do I have in this one?
Yeah.
No, I think it's 1.5.
Yeah, 1.5.
So we go top, bottom, top,
Oh, yes.
and then top to bottom. So it's 1.5. So that's 3/2. So here the wavelength is 2/3 D. Are you talking about your maths exam?
I don't want to do any math.
What?
I don't want any math.
Okay, good. Continue?
No.
Yeah. Oh, Grace, come on. Okay.
One and half.
Yes. Yeah, got that? Okay. Okay. Um, Right, anyways, we drew that plenty. So let's have a look at an example. Let's see what I got. Yeah, I've got two examples to do. So first question, can you write this down? So a boy ties a 2-meter rope against the wall and he vibrates the other end so that a first harmonic, what's another name for a first harmonic? Fundamental is formed. What is the wavelength of the formed wave? Okay, try this. Now I say in the question that the rope is 2 meters, but really I mean that the boy is 2 meters from the wall. Fundamental is a wave, yes.
The biggest
The
one.
biggest wave.
Biggest.
Yes.
Harmonic.
Harmonic
Harmonic
is the next one, the smaller wave.
half of the.
Sometimes half, but maybe not half. It's just the next one.
What is the next one?
Also harmonic. The next harmonic. The next harmonic.
The first one is bigger.
Okay, can we have a look at this now? Okay.
This one is bigger.
Is that open and closed or open and open?
Open close.
Yeah, so the first one that just goes middle to top is biggest, yeah. Alright, here's the boy, and here's the wall, and I said the rope is 2 meters, but I really mean that the boy is 2 meters from the wall. And it's tied here. So the fundamental is the biggest wave, the biggest standing wave he can make. So what's the biggest standing wave he can make?
8 meters wavelength.
Very good. He's super fast. So if he's fast enough, he can make a wave. How big would the wavelength be?
8 meters.
8 meters.
What is super fast?
That he can take the rope and he can go up and down like this. However, if you don't think the boy is super fast, if you just think he's super slow, what you could do is he could hold the rope here and here, and then just give it, like for example, if you don't think the boy can do this fast enough, then you can at least say, well, he can hold the rope here and then put the other end on the wall and then pull it up and then let go. So then you'll have just one hill. So then what would be the wavelength here?
1.
4 meters. Yeah.
1/length, so.
Yeah, because this, you would have half a wave. So it depends on your opinion of how fast you think the boy could be. So really it's 8 meters, but if you want, and you could say, no, you can't move it that fast, then you at least have to say 4 meters, because you can hold the rope, and then someone can, or he can pull it up, and then it can move up and down like this. But I'm going to go with 8.
And this answer is not true.
Yeah, I didn't say in the question. Let's say he's flash. Then it's 8 meters. Okay. You all know Flash, don't you? You know Flash? Are you sure?
Yes.
She knows Flash, of course. Friends with that man. Yes. Alright, next example. Yep. This one here, the person who writes the exam at the moment, he's asked this question, I think maybe 3 times in the last, 5 years. So this is the type of question you would get in an exam about standing waves. Okay, can I go on? And by the way, there's something I actually, not that it's super important, but it's good that if I at least say it here. Oh, I'll draw it. I'll go back here. Come on. No, I'll draw a new one. So, for example, if I have a fundamental, it will look like this. Yes? Come on, look. How are you? But of course, it's vibrating up and down, so it's vibrating up and down here, and it's not vibrating here. If you put some sand at the bottom of the pipe and let the sound wave vibrate, after a while what you'll notice is you'll have kind of some pile of sand here and then not much sand down here. Why do you think that happens? The wave pushes it, yeah. Because this is moving so much, the sand here, it doesn't stay in that spot. But because this is not moving, it means when the sand falls over here, it just stays there. So you can actually put some sand in the pipe, and then if you have the sound in the pipe, you can start to see the sand making little piles in the pipe. Yeah. Anyways, back to the question. So this question here, Usually we draw the pipe standing up, and it's closed here, and it's open here. And what did I say the length was? 17 centimeters. And what type of standing wave do we have?
The
Fundamental. So I should draw it like this. And it's vibrating the most here. And what's the frequency of the sound wave? What did I say? 500. Now you can make a sound wave the old-fashioned wave by using a tuning fork. Have you seen these before? You know, you hit them on the table like this. But of course nowadays I could go to YouTube and type in 500 hertz sound wave and I get it. But old-fashioned way is with the tuning fork.
How do you know it's 500 hertz with the tuning fork?
They're like weights. They come in a pack, and each tuning fork has a different frequency. So you just pick out the one that you want. But I mean, nowadays you can do this digital, you know. So even just YouTube, 500 hertz, and you get the sound wave coming out. Put it on your phone. Put the phone beside the pipe. You know. Now there's an idea. Have you got a ruler?
No ruler.
Yeah, I wonder how this would work. It is 10 centimeters. We'll get back to this idea in a moment. Don't drink any water. Okay. How big is the wavelength here?
40.
Yeah, so the wavelength here will be 4 times 0.17, which would be 0.68 meters. Now I want the speed of this wave. So what formula could I use? V equals F lambda. So that would be 500 times 0.68, which would equal, what would it equal? I think it should be 330?
340.
340. Yeah.
Now that sound, the speed of sound waves are the same.
Yeah, it doesn't change so much. It depends on the medium it's in, but in air, still air, should be 340. Can I go down? Okay. Yes? Right, so here's Amanda's drink, and there's some water in it here. This distance here is 10 centimeters, and we want to make a fundamental standing wave inside of it. The sound wave, its velocity is 340 meters per second. I think it's actually more like 330, but we'll go with 340 for the moment, and 10 centimeters. So I want the frequency. So V equals F lambda. What does F equal? V over lambda. But what does the lambda equal? What's the lambda, the wavelength here?
40.
Very good, 40 centimeters, isn't it? So can you tell me what 340 divided by 0.40 is? 0.4, yeah.
It's 850.
50 hertz. Okay, can you take out your phone? Amanda? You got your phone? And can you type in 850 hertz sound wave into YouTube? You got your phone? Or you got your phone? Phone, yes, YouTube. Yes, YouTube. 850 hertz sound wave. That doesn't sound like a sound wave. Yeah. Oh. Is that 850?
Yep. No. 880.
Open that, please. Can you take the top off? Can you, we'll open this?
Yep.
Put it on the top. Let's see. No, don't touch them. Not strong enough. Nah, not strong enough.
800.
No, the frequency is right, but it's not strong enough. It's too quiet. So anyway, what I wanted to show you, but I can't, I tried, I can't. If you could do this, what you would see is the water would shake. The bottle would shake. But the problem also, of course, is the table is also shaking. So I can't tell if it's the table or if it's the sound wave. But you get, this is what you would do here. Well, let's try again, but with maybe bigger speakers. I could also do it with my coffee cup. But I don't want to move it. So I hope you're not thirsty. I'll put it here. Don't want it to move is the problem. So we'll make it shake and then no, not that part. Good, okay, so it looks like it's not shaking right now. Can you see it?
Yeah.
It's not moving. Let's get some movement on it. Okay. Oh no, you didn't get your laptop.
No.
They didn't have it.
I don't know. Maybe I will go for today.
Okay.
I don't know how to say.
Can I have my laptop?
Yeah, exactly.
No, just they are working and some people says, can I get a laptop? They were confused. What happened?
You can practice your English. Okay. Let's see.
Whoa.
Maximum power. No, too loud for you. Alright, I won't do that.
You close our ears.
That's cruel. Okay, no, I can't get this to work. The nice thing about a tuning fork is that you can hit it really hard and it makes a very strong wave, and you can put it right on top. The speaker on the phone is not strong enough. Anyways, let's try it. There is another one I can show you here. So, you see here, there's the picture of your eardrum. You see it there, look? The picture of your ear? So this is closed at one end and open at the other end. So if I have a standing wave in here, the wavelength should be 4 times the length of your eardrum. So you see how big it is? 2.5 centimeters. So what's 4 multiplied 2.5? So that's 10 centimeters, yeah? So if I go back here, if I change this to 2.5, or well, here, we'll draw it like this. Here's my ear. Ear.
No.
Yeah, it is. Look at that ear. And then here's my head. Oh, yeah. Head. I want to make a wave here, a fundamental. This is 2.5 centimeters in my ear. So the wavelength would be 10 centimeters. So the frequency, you have V equals F lambda. So frequency is V over lambda, which is V over 10, which is 340 over 10, which is 3400 hertz. Now I don't quite think it's 340, but I think it's about 340. So if I just hear speed of sound, yeah, 340. So if I play this frequency, it will make your ears shake. So if you want, you can cover your ears now if you don't want to hear this. But if you want to know what this sounds like when your ear shakes, you can listen to this. Oh, okay.
Oh, my head is shaking.
One more time. It's only 10 seconds. That's not too bad. No, it is. Now, the thing is, each of us will have different sized ears. So, for example, my ear will be a little bit bigger maybe than your ear. So it'll be about 3,400. So if that was okay for you, you could try 4,000. So for me, that's more painful. For you, the same or less?
Same.
The same? Yeah. So it's because each of us has different sizes, but you could find a frequency that would make your ear shake, and this would be most painful. But it's different for each person. Okay, let's have a look at some questions now. Right. Victor?
What's this?
Homework.
I can't see anything.
Yeah. And you can't hear anything now either, yeah? do these for a few minutes, and then I can do them. And then if we get them finished today, then waves are finished, and that's everything for the test on Tuesday, Monday? Tuesday, yeah. So this is the last topic that can be on your test, okay? Do test is on Tuesday. Do you want to do more revision in the next class, or do? Okay. Let's see the other students' opinion. Would you want to do some more revision before the test?
Yeah.
Yeah? Okay. So we'll try and get this finished today. I want you to try and do these now. Question 1, 2, 3 and 4, they're all quite short, but 5 and 6 is a little bit difficult. Now that means I want you to try it, but it's a little bit difficult, okay? So can you do these for 10 minutes and then I'll do them. Now I need to close the screen. So have you got it on your phone? Yes, can I close this?